Good morning, John. Suddenly, along with the disaster in Japan, has become kind of necessary to understand a little bit about how nuclear reactors work. And so I hope that you will excuse me postponing my thoughts from Haiti and instead giving an introduction to how nuclear reactors work and how that pertains to the situation in Fukushima right now. So first things first, you are welcome to say nuclear, but you should know that there will always be a certain percentage of the population who will assume that you are a dumbass. I personally have no problem with nuclear, but if you want fewer people to think you're an idiot, probably should just switch over to nuclear. Now for terminology. 1. Nuclear. Pertaining to the nucleus, which is the center of the atom that contains the protons and the neutrons. Nuclear reaction, a reaction that changes the nucleus. This happens either by an atom splitting apart or by two atoms fusing together. Radiation is any particle or wave that goes through the air or goes through other things besides the air, like your body. But generally, when we're talking about nuclear radiation, we're talking about ionizing radiation, which is the kind of radiation that has enough energy to ionize an atom. Radiation can be harmless, but it can also be not harmless. Radioactive decay, this is important, it will come up again soon, is when an unstable atom loses energy by emitting radiation. Fission, when an atom breaks apart into two or more atoms that are an entirely different kind of atom than the original atom. During fission, a great deal of radiation and energy is expelled, and the fission products, which are whatever's left over, are always lighter than the original atom. Now, where did that mass go? It was converted into energy in a way that is described by a very famous equation. Notice in that very famous equation that we are multiplying by the speed of light squared. You may have noticed the speed of light. Very big number. And so when you convert a tiny amount of mass into energy, you get a great deal of energy, which is why, something in my ear, a pound of uranium-235 can be converted into as much energy as about 1 million gallons of gasoline. Speaking of which, uranium-235 is a rare isotope of uranium that has very unique properties. First very unique property, when you hit it with a neutron, doesn't even have to be a special neutron, it fissions. Second, when uranium-235 splits, it creates more neutrons, which then go on to hit more atoms of uranium-235, which then go on to create more neutrons, which then goes on to create a chain reaction that can be turned into either a nuclear bomb or a nuclear energy reactor. So in a nuclear power plant, you have uranium-235, and you have it mixed into these ceramic pellets. And through the majesty of science, these little guys can never explode like a nuclear bomb. These pellets are placed into tubes of zirconium alloy that is extremely strong and heat resistant. That tube, with uranium pellets in it, is what we call a fuel rod. When a bunch of these rods are placed together, the uranium begins to fission, creating energy and radiation and neutrons and fission products, which are the stuff that's left over after the uranium splits apart. All of this stuff is what is called the reactor, and it's encased inside a thick steel box, like 8 inches thick steel. That steel box is called your primary containment, and then that is inside of a giant concrete and steel box, which is your secondary containment. So in the reactor, the fuel rods are hot, water is pumped through the fuel rods, it turns into steam, the steam drives the turbine creates electricity, and that is how we get electricity from nuclear power. Now, if we want to turn it off, we have what are called control rods. Control rods absorb neutrons. You stick them in between the fuel rods, and it absorbs all the neutrons. No neutrons are left to continue the chain reaction, and the reaction stops. Ideally, that would be where it ends, but it's not, because we have those fission products. All those fission products left over from the uranium splitting are unstable isotopes, and this is where we come back to radioactive decay. Because they are unstable isotopes, they decay, and as they decay, they produce radiation and energy, and that energy becomes heat. And it's not nearly as much heat you get in the center of a reactor when it's running, but it is still a lot of heat. In fact, it is so much heat that if you don't cool it down, the fuel rods themselves will eventually break, and you will have what we call a meltdown. And this is what happened in Fukushima. As soon as the earthquake happened, the control rod slammed into place, the reaction stopped, but we still had the fission products creating a lot of heat. The grid power immediately got taken down by the earthquake, and the backup diesel generators, they got wiped out by the tsunami. And so there was nothing left to power the coolant system, the system that keeps water running through the reactor so that the fuel rods don't get too hot, they don't break, and they don't melt down. So it appears that some of the fuel rods did break. That created an environment combined with the heat that could actually split water into hydrogen and oxygen, creating hydrogen, which we all know is explosive. And we've seen the effects of that in a series of hydrogen explosions throughout the plant that have damaged both the primary and the secondary containment at least one of the reactors. Additionally, just like the reactor when it's turned off still produces heat, we have what are called spent fuel rods. These are fuel rods that no longer contain any uranium, but they do contain all of those radioactive fission products. Spent fuel rods can spend years at the bottom of giant pools while we wait for the radioactive materials in them to decay enough that they are not producing so much heat that they cannot be dealt with in a different way. And the same way that the cooling system for the reactor isn't working, the cooling system for those spent fuel rod pools is also not working. There's another difference between the reactor rods and the spent fuel rods, and that is that the spent fuel rods do not have a primary containment vessel, so there is less protection, and if the water in those pools boils off, the spent fuel rods could melt down, create a fire that would spew radioactive dust into the air, and it would be bad. The men and women who remain at the site trying to keep the situation under control are very literally risking and possibly sacrificing their lives for their country. Those men and women are made of some tough stuff, and I wish them a great deal of luck in getting this under control. You'll notice that throughout this video I have not been making judgments about whether or not we should be using nuclear power. That's because I simply do not know. I can see and understand both sides of this argument very well. I do not know whether or not the benefits of nuclear power outweigh the risks. I do know that most of the ways that we generate the majority of our power now are dangerous and bad, but that we need electricity for our society to function and for people to be happy and healthy and safe. Quite frankly, I think it's kind of ridiculous that so many people seem to have made up their minds about this issue when, obviously, it's a very complicated one. It's almost as if our society values opinions more than it values knowledge. I can only hope that this situation simply doesn't get any more severe than it already is, and that the people working at their plant and the people living nearby are able to safely return to their homes in a relatively short amount of time. And I hope that people who watch this video can understand a little bit better the situation and not panic unduly. John, I will see you on Friday.